Hey guys, Mr. Gron here with another challenge video. So 8-6 day 2, we're going to be dealing with rational exponents, so fractions with exponents. Exponents with fractions. Okay, now this one doesn't have exponents or fractions for exponents yet, but to do this, one method that I think is probably one of the easier methods of doing this involves converting this to rational exponents. So pause if you think you got it, otherwise unpause and let's see how this one's done. Okay, so the first part, I'm going to sort of go from the inside out, so like onions, right? Lots of layers. I'm going to go with the innermost layer first, this square root of x to the 8th. If I rewrite that as a rational exponent, then that would be 8 over 2, right? Because the square root is an exponent of 1/2. Okay, so that's kind of the equivalent to that innermost layer. Then the next layer, we're taking the cubed root of that inner layer. And so that means we are taking this, the yellow part, and we're raising it to the 1/3 power. So that 1/3 power represents that, the orange radical. And then the outermost layer is the square root of everything, which would be raising to the 1/2 power. So that's what that 1/2 exponent represents. Well, now, if I apply the power of a power rule, I can multiply all these exponents. Now, we can reduce this 8 over 2 first. You don't have to, but it might be easier to look at. Make for some smaller fractions if we change it to x to the, I'm going to make it 4 over 1, just so that it's, anytime I'm working with fractions, I like to have everything be fractions. All right, so now power of a power rule, or in this case, power of a power of a power, says that this is equal to x to the 4 over 1 times 1 over 3 times 1 over 2, which is x to the 4 times 1 times 1 on top is 4, 1 times 3 times 2 on bottom is 6, and if we're going to simplify it, we may as well reduce that fraction to 2/3. All right, so see if you can employ a similar strategy to solve a slightly more complicated one than this. So if you want to pause, otherwise unpause when you're ready, or just keep watching. Okay, so again, I'm going to go innermost layer outward. The innermost layer on the left-hand side is a to the 12th, and so the square root means it's 12 over 2. Then the next layer is another square root, so that's to the 1/2, and then another square root, so raised to the 1/2 again. Then the one on the right-hand side, I guess there's a big set of parentheses around all that maybe. Same thing, only now it's divided by 3 because it's cubed roots. So a to the 12 over 3. Take the cubed root of that, and take the cubed root again of that. Now, why don't we reduce some fractions just to make this a little bit nicer to look at. So 12 over 2 will be 6 over 1 times 1/2 times 1/2, and that we are multiplying by 12 over 3 would be 4 times 1/3 times 1/3, like that. And so the left-hand side now is a to the 6. 6 times 1 times 1 is 6, and then the denominator is 1 times 2 times 2 is 4. And the one on the right-hand side is a to the 4 times 1 times 1 on top is 4, 1 times 3 times 3 on the bottom is 9. And we've got another fraction that we can reduce. So we can convert that to a to the 3 over 2 instead of 6 over 4. Okay, so now we are trying to multiply two bases. In that case, we add the exponents. So that is going to be a to the 3 over 2 plus 4 over 9. in order to add these, we need to make a common denominator. The common denominator, the least common denominator between 2 and 9 is the same as 2 times 9 because they don't share any common factors. And so that is going to be, if we multiply the 3 over 2 by 9 over 9, would be 27 over 18. And if we multiply the 4 over 9 by 2 over 2, it will be 8 over 18, which gives us our final answer of a to the 35 over 18, which my sources tell me is not a reducible fraction. All right, last one. This one's actually doesn't look as daunting, but there's a little trick to it. And if I'm going to give you a hint here, it would be to think of what happens when you multiply a decimal number by a decimal number. What happens to the decimal spaces? All right, so when I figured this out, I actually like to convert this the other way and think about this as the cubed root of 0.0227, that quantity squared, where we can square it on the outside. We don't have to square it on the inside. Like this and this are the same thing, it turns out. Okay, so when we do this, if I start to like break down 0.027, I notice that 27 is a perfect cube. And so I feel like that would be a good place to start. And then now what's left? If I divide out a 27, then what's left is 0.001. Like 0.027 is equal to the product of 27 and 0.001. Now if I continue factoring, 27, hopefully we can factor. It would go to 3 and 9, and that goes to 3 and 3 because it's a perfect cube. But what about the 0.001? Well, I could split this to 0.1 and 0.01. You might see the pattern here. 0.1 times 0.01 creates when I multiply that by that, I get 0.001. Well, now, if I split this up again, that is equal to 0.1 times 0.1. And like the first way that you learn how to do these, you make factor trees and look for groups of 3 to make that perfect cube, because it's 0.1 times 0.1 times 0.1. That means the cubed root of 0.001 is 0.1. And so the cubed root of 0.027 is the product of 3 and 0.1, which is 0.3. We've still got the squared up here, so this is equal to 0.3 squared, and 0.3 squared is 0.09.